I'm ready to introduce our featured speaker, Sar Garfunkel, who I've known and admired for many, many years. Saul earned his PhD in mathematics at the University of Wisconsin way back in the 1960s. And in 1980, he became the founding director of the Consortium for Mathematics and its Applications. For 40 years, this has been an organization that has promoted the use of applications and especially modeling across the mathematics curriculum. Many of you know it for the mathematical modeling contests that it runs, both the undergraduate contest and the high school mathematical modeling contest. Many of you know it for its many publications, for its journal, the COMAP journal, and all of the resources that the COMAP has made available to people over these 40 years. It's a great honor and privilege to be able to introduce Saul to you now, and look forward to hearing what he has to say. Saul, over to you.
Okay. Share my screen. Okay. That's me. Made an introductory screen. So let me start by just talking about what we've been doing for the last 40 years. As David's mentioned, our mission for these 40 years, by the way, almost to the day, remains the improvement in the teaching and learning of mathematics for all students through the use of contemporary applications and mathematical modeling. We always wanted to be the answer to what's this stuff good for, to show people what mathematics was in fact, why we study mathematics essentially every year of school. And you know, the answer can't be to simply improve your mind or whatever. The answer is because it's useful. And it's useful day to day. It's useful throughout life. I mean, it is a life skill. Now, so everyone talks about mathematical modeling now, which is very nice. We worked with SIAM to produce this game report, which I hope many of you have seen, which stands for Guidelines for Assessment and Instruction in Mathematical Modeling Education. We stole that title from the GAZE report by the American Statistics Association, a wonderful document if you have a chance to look at it, which is Guidelines for Assessment and Instruction in Statistics Education. And we began, the whole purpose of the game report was to say, well, what is modeling? How does it differ? Why do we do it? What are examples? It's not word problems, it's more than applications, it's a process. And so we start with this definition so that people are all on the same page, which says that mathematical modeling is a process that uses mathematics to present, analyze, make predictions, or otherwise provide insight into real-world phenomena. The point about modeling is it starts in the real world and it ends in the real world. You start with an honest-to-God problem that you care about and want to solve. You go through the mathematical analysis to try to get a handle on what that problem might look like, or at least what math can tell you about it. And in the end, you come back to the real world. And if you didn't do it well, or if the analysis doesn't make you happy, you come back again, because in order to do mathematical modeling, you have to make a lot of assumptions, and you may have oversimplified the problem. But the point is that modeling starts with a real problem, ends with hopefully a real solution. So, how did we do this? Well, we made stuff. I like making stuff. We began from the very beginning with undergraduate material and moved into high school material. We've done some elementary work, but basically we've produced student and teacher materials, as I said, mostly at the high school and undergraduate level, in whatever format we could get our hands on. So in print, in video, and multimedia, ranging from individual lesson length modules to week-long modules to television courses to full high school 4-year textbook series that we've done. Again, the question was, what was useful? What could students and teachers use to learn mathematics through these contemporary applications and through mathematical modeling? So why? Well, I guess I said something about that. Okay, there is no doubt that when you start with an interesting real world problem, you engage students in mathematical activity, so that time on task helps a great deal when you're dealing with something that's inherently interesting and a problem that kids may see a reason for wanting to solve. But it also is, it helps with their understanding of the world around them. I mean, the point is, mathematics is inside of their cell phones. It's inside of the technology that they use. Of course, it becomes invisible to students, but the point is we need to make it visible. I mean, they don't have to learn data compression in order to understand how their phone works, but without those algorithms, they wouldn't have that phone, right? I mean, so this is what makes the world work, and they need to see it. And so that's why we teach mathematics through modeling. And as I said before, it's also a life skill. It's you want to hang pictures on a staircase so they look straight. That is a non-trivial problem, but you might have to actually do it. You can use mathematics every day. So it's a process. What do I mean by that? It's not, we don't teach mathematical models. Take this model, okay, you've got a problem in epidemiology, reach up on the shelf, pull off your epidemiological model and plug it in. That's what we're studying today. That isn't the point. Yes, we'll teach modeling through the process, but it's it's the students owning the mathematics that's crucial. It's not teaching them someone else's mathematics. Of course we do that, but they need to have a sense of ownership to look at the problems. Modeling allows students to use their own experiences, their life experiences, and that enables them to feel that they're part of the mathematics, which I think is crucial. Game talks about this in a great deal, but I mean, when the Common Core first mentioned modeling as an issue, people would come up to me and said, I need modeling. Do you have a pound of modeling? Can I buy a couple of board feet of modeling? No sense of, it isn't about, right? It's about the process for students to go through, to understand, to make their own assumptions, to bring their own knowledge to bear on the problems. So in addition to the curriculum materials that we've developed, as David indicated, we've also created several mathematical modeling contests. And I raise that right now because the contests themselves give you a good example of the uses of modeling and in the real world. I mean, the difference of these contests, and I should say the first contest was the MCM undergraduate contest that was funded by FIPSI in 1985. We added an interdisciplinary contest in 99, in which the problems involved a little bit more knowledge of specific disciplines like environmental science. In 99, we also added the high school modeling contest, and then just 5 years ago, the International Mathematical Modeling Challenge, which is more on the line of the Olympiad, where only 2 teams per country are allowed. Now, each of these contests share several characteristics. They are team contests. The undergraduate contest, MCM and ICM, are teams of 3 undergraduates. In the high school contests, we allow teams of 4. So that this is not a pencils up, pencils down, the doors closed, proctor is making sure you don't look at anyone else's paper. This is an honest to God team contest. And again, why do we do it? We do it because in the real world, people work in teams. They work together on problems. An additional factor in these contests is that they're not timed as tightly, so that the undergraduate contests are given over a 4-day weekend, and the high school contests, while the problems are designed to be done in 36 hours, we give a 17-day window, in the case of IMMC, even a bigger window, to find that time, so that we don't restrict. Time is not to be the problem. And again, in the real world, when you solve problems, no one is sitting, well, they might say you've got a couple of months, but the point is you have time to work on these things. And in addition to that, these contests allow any and all inanimate objects, inanimate resources. So if someone wants to use the internet's fine. You can use libraries, it doesn't make any difference. You can look up anything, anywhere. The only restriction in these contests is that you're not allowed to ask someone not on your team how to solve the problem. Now, again, we do this because it reflects the real uses of mathematics when students leave. We've asked students about this. I should say, I know that equity is a big issue in the conference that we're in. I won't claim that we did this on purpose, but the net effect of this type of approach has been that we've had a historically very high percentage of female participants. So it's not perfect, but we get 43.5% of the students who work on the contest are female. And in addition to that, what's really lovely is that essentially the same 43.5% are on winning teams. So if you look at the teams that make outstanding, which is our highest award on these contests, the outstanding teams, 43.5% of the participants on outstanding teams are also female, which is again how it should be. Not the percentage, but it should be the same percentage as the number of people attempting these problems. And I want to make clear that we didn't create these contests with the purpose of rewarding bright kids, although that happens. We did it so that we could affect the teaching, the courses in preparation, showing people what modeling can do, show what kids can do if they're given open-ended problems. We did a little research project with Joe Bowler of Stanford about the participation of women, and we asked people why they participated, and it probably isn't a shock, but one of the key reasons that the female participants gave was the fact that it was a team contest, that people were working together. The other thing, of course, was about the nature of the questions, the fact that they were real problems, the fact that they could look at this work and say, you know, I always wanted, people told me to study mathematics, it would be good for me or would help me in one way or another, but now I understand what mathematicians do, what kinds of work there really is. Okay, so this is a talk about modeling. I guess I've said all of this. Well, no, make one more point. Okay, so the other point I want to make here is that when you work on a real problem, it doesn't come at the end of a chapter in a textbook. If you even a textbook that's got lots of good examples and applications, if the problem comes at the end of a chapter, the students know they're supposed to use that mathematics that was in that chapter. That's not the point here, because real problems, first of all, they may or may not be mathematizable easily, but second of all, We don't know what the math is that will be used, and often they're going to have to apply algebra, geometry, statistics, a whole variety of topics in order to analyze and solve those problems. Okay, as I said, a talk on modeling without giving any problems is very dry indeed. So let me give you some examples. Actually, I'll give you one example that's not up there, which is one of the MCM problems. Actually, it was the first year that a high school team got the outstanding award from the undergraduate contest. And it was a drug running problem there. We don't run drugs, but there was, the nature of the problem was there's a boat off the coast of Florida. It was suspected of running drugs. You, with the Coast Guard, you had a helicopter. You send the helicopter out to try to find the boat. And the question is, what's your optimal search pattern for that helicopter to look for the boat? And we gave the speed of the boat and the speed of the helicopter and how far away the helicopter was when the boat could hear it and so on. And the team from the North Carolina School of Science and Math, which wound up being the outstanding team, one of the outstanding teams, was the only team that recognized that you didn't have to find the boat. You could look for the wake of the boat and follow the wake to the boat. So it gave it a much bigger area, search area for this helicopter. There was no particular advanced types of mathematics being involved in that analysis. And that's a point I want to make. We don't value specifically the use of higher level mathematics. In fact, in modeling problems, it's crucial to use mathematics that you actually understand at whatever level that is. Okay, so some of these other problems I'll just give quickly. The first one, Iota Henry Pollock, we used it in our Mathematics Modeling a World High School program. This was, you've got a certain number of athletes, you want to test them. In this case, we used anabolic steroids, but you could do it with a disease, you could do it with underground pollution. You want to test them, and the question is, at what percentage of drug use in the population does it pay to pool the samples and test the pooled sample? Clearly, if only a few people are taking the drug, most of the tests will be negative. We'll assume perfect tests for this problem. If they're negative, you get away with one test instead of two, by doing it individually. If it's positive, you may need 3 tests. At any rate, what's nice about this problem is for 2 athletes, by the way, all modeling problems get interesting at n equals 2. This is meta theory. So at n equals 2, at 2 people, this leads to a quadratic. It leads to actually a non-factorable quadratic, and it's x squared minus 3x plus 1 equals 0. And this is the first time in the middle high school program we developed that students see a quadratic. And it's not an area problem, it's not a square versus a rectangle, it's an actually nice problem. And not only that, if it's 3 people, it leads to a cubic. If it's 4 people, it usually gives you a quartic, and so on. You can introduce higher level polynomials with this question. And if you allow testing of smaller groups, not necessarily n versus each one, this is an unsolved problem because it turns out to be a coin weighing problem, and it turns into a problem that is not yet solved. In game, we had this example of how many miles you're willing to drive to buy gas at a lower cost. Looks trivial, but it's not, because you know, time is important, time of day is important. It's not simply a simple calculation. So students have to think about what their constraints are. Here's one about a bank of elevators in a building. Elevators tend to have one of 2 programs. One leaves them where they drop you off and then go back down when they're called again, and others send the elevator right back to the lobby. You want people to get to work on time. How do you program this thing? Does it depend on the time of day, rush hour, so on. Massachusetts, where I happen to be these days, is going to have a referendum on preferential voting. You can't believe how much they've tried to explain it, but what does it mean? And do you vote for or against it? This problem, next one, was given originally for Michael Jordan, but I'm trying to modernize it. So let's imagine that LeBron James is fouled and he goes to the line and the announcer says he's shooting at a free throws at a rate of 78%. He goes 1 for 2. And then he's fouled again in the second half, and the announcer says he's now shooting 76%. Does that make sense? And how many free throws has he taken and how many has he made? It's not really 2 equations and 2 unknowns. It's actually 4 inequalities, right? Because everything is being rounded off. Some problems from the last IMCM that we had, just to get back to reality. It's a plug-in world. You know, you've got a phone you've got to plug in, you've got a car you've got to plug in, you've got a computer you've got to plug in to charge. Who's paying for that? How much money is at stake here? What sense does that make? It all seems like it's for free, but it's not. And this one was also from our high MCM problem, which was a joy. Kids liked it. There's the roller coasters. The roller coasters are rated. They're rated about, you know, what are the top roller coasters? Well, what does it mean to rate a roller coaster? Is it scary? Is it fun? Is it, you know, dangerous? And there are ranking systems, and we ask the students to try to invent their own ranking system. So there are an enormous number of problems. Literally, we have thousands. We have material which just has the problems. We have material with some solutions. We have material that develop it from scratch. And there is no end to the kinds of things that students are interested in and that are available to you. I'm just laying out some of the COMAP stuff. The modeling hub has also, is going to have more material on it. Our resources can be found at the website, www.comap.com. There's also a mathmodels.org website, which has all of the contest problems. They're free. There's a small charge if you want to see solutions, sample solutions. The list here of free materials that are available from COMAP, and also, of course, COMAP membership gives you the right to download any and all things that we've ever made for free. So the idea, there's lots of stuff. It's not hard to find. It's just a commitment to teaching mathematics through modeling, and it's something I think that its time is now, and I welcome any and all questions. So I'm going to stop sharing my screen, and I guess David is going to see what people have asked about, and I will open up.
Great. Thank you so much, Saul. You mentioned in your closing remarks that you think that the time is now. You know, this is something that you and many of us have been working on for many decades. What do you see as special about this particular time that you think can really move people toward doing much more emphasis on modeling within the curriculum?
Well, there's no doubt that when the Common Core started to talk about modeling, that was extremely helpful. I think people started to ask themselves, what did it mean? I also do think that the equity questions start to play here. The idea of using mathematics in the real world. I've been part of a number of projects that looked at the disconnect between the mathematics that we've been teaching, both at the high school and the two-year college level, and the mathematics that people were actually using on the job. I was involved in one project which was called the Needed Math Project. And this project brought together two-year college educators and also industry representatives. And in particular from biotech and manufacturing and IT. And they said a funny thing. The industry people said they shared their problems and they shared the types of questions that they needed students to work on or incoming workers to work on. But they said something that was very disturbing in a sense. They said that their employees knew the math, they just couldn't use it. And I tried to, figure out what that meant, unpack that. And what that meant was they passed a college algebra course. These companies had money. They could afford to hire people who got good grades in appropriate courses. And college algebra was one of the courses that they wanted them to take. So these were students who had A's and B's in a college algebra course. And when they gave them a job to do, they could train them to do it, and then they tweaked that job, especially say something like biotech, where they had a certain mixture problem that they were dealing with, and now they had a slightly different mixture problem to work on. Their employees saw that as a separate and new problem, as opposed to just a relatively simple switch from the problem that they'd already been working on. But that's because they didn't understand. They could solve certain equations. They could pass an algebra 2 test, but they couldn't use the material and they couldn't work on the job. And so they were asking for help in those kinds of ways. They use the passing of certain courses as a kind of, bar. Okay, you got the eagle feather from the mountain, and therefore, it's a puberty right. You've done something, but they weren't able to work and do the job. So I think that more and more we're hearing that from companies, and there are more and more about, I'm not saying that we're a vocational training, but the idea of using mathematics, of being able to understand its role, I think makes all the difference. And at heart, it is about modeling. At heart, it is about modeling. I think there's just a wider recognition. And I also do think that, you look at the pathways issues and others, there's an awful lot of wonderful, good mathematics that underlies some of the most important developments in discrete math, graph theory, game theory, all of these things that are accessible. First of all, they're interesting. They model interesting problems. And second of all, they're accessible to students without an enormous amount of machinery that has to have been built up. So I think there are a lot of factors that are coming to bear at the same time. And I think modeling is it's about to have its day. Yeah, I hope so.
Thank you. Yeah, I hope so
It
too.
should happen. 40 years, nothing good should happen, right?
Yeah, well, want to point out that Rachel Levy has posted a couple of links in the chat, one to the Math Modeling Hub and the other to the game report. One question, how do you see computer science and mathematical modeling working together?
Well, on a personal level, I think that we should have a curriculum that is called the Mathematical Sciences K-12. I think the idea of separating mathematics, computer science, statistics at the K-12 level is silly. I think we need to combine these things and look at, it's not, so one of my pet peeves about the Common Core is it left a lot of the statistics to 7, 8, and so on down. I think we started at grade 1, grade 2. I think people should see this all together. It's one piece. And I think we separate it for historical reasons, and it's hard to change because of that. But I would like to see a mathematical sciences K-12 curriculum. I think that's something worth working on. Instead of thinking, okay, you do this up to this point and then you do this. No, no, no. You can see, you should be seeing these ideas early on and seeing them connected, as opposed to, you know, I always use this analogy of, okay, we're going to teach students to hammer a nail for 6 years, and then going to teach them to saw a piece of wood for another 5 years. And there's this thing called a house, and you'll build it, but not yet. Wait till you build up all these technical skills. No, no, no. Delayed gratification doesn't work. I think we should be showing this all the way through. So I think the answer is from day one.
Yeah. Well, related to that, from Kendall Brown in California, doesn't this all speak to a need to overhaul pedagogy at the post-secondary level?
Absolutely. I mean, absolutely. I mean, I'm not sure you can get me started. I once got into huge amount of trouble from the mathematical establishment when I wrote a letter to the editor in the notices and suggested that a PhD in mathematics was not sufficient to get a teaching certificate at the college level. You can imagine what came down, but I think that's true. Yeah. I think for many places, getting a PhD is, and doing good research, which I value, but doing good research is, in fact, all you need to do to be an undergraduate teacher. But in fact, you need a great many more skills that we don't necessarily teach or value at the undergraduate level. So absolutely, absolutely, it starts there. I mean, these are undergraduate, you know, it's a cycle. These are the teachers who teach, right? And so you've got to break it at every possible level.
Oh, and related to that, from Uri, how do we build the capacity to teach the mathematical sciences to all of our students, both undergraduate and K-12?
So he would ask a tough question. If I knew the answer to that, I'd be like, no, again, I mean, I think you have to, building the capacity. First, you've got to motivate, you've got to change attitudes. That's at the start. There's an awful lot of talent out here. I mean, I look at the people whose names come across this screen. I look at the people at Dana Center and the people I work with. There's a lot of talent. It's just got to be organized. It's got to be valued. It's got to be put together. CBMS, I think, is the right organization, among others, to do this. I mean, I think you've got to, look, this kind of a revolution, you have to have top down and bottom up. You have to do both. And, you know, and you've got to put resources, behind it. A lot of resources behind it, but it's the only way to go. It's going to happen. I see it in other countries. Some of you know that in the modeling contest, we have a huge number of Chinese participating teams. And that is in part because China has decided that modeling is the way. And they have now moved that into their high school test. You know, China, like a lot of countries, has one of these end of high school exams, which really are high stakes. Believe me, in China, it's high stakes. It tells you whether you get into college, what school you'll go to, and so on. But now there's modeling on there. And this is a huge commitment. You know, it's no secret that it's what you test, what you value. And if those exams have significant amounts of modeling, and I know it's hard, I know it's difficult. I know Doug, when he was working at Park, had to deal with this question of how do you teach modeling in a serious, test modeling in a serious way. Nonetheless, if you value it, you test it. If you value it, you reward it. I think it's very important. But it's a major effort. There's no shortcut to doing this.
I just want to mention that there are lots of comments coming in on the chat, agreeing with you and supporting what you're saying. Talking about the assessment, Rachel Levy asks if anyone is aware of performance-based assessments with authentic modeling tasks.
Well, we have some. We have a modeling handbook that we did with the people at Teachers College, Columbia, which has a significant number of assessments with authentic problems. There's some in game, but yes, I mean, the answer is there is material. There's also a fair amount of material, by the way, from our foreign friends. The material work that's done by Werner Bloom in Germany and by Mogens Nis in Denmark, Gabriela Kaiser in Germany. So there are a number of things that have been done in a serious way on assessment that you can find in the literature. There's a growing body of literature on the effects of modeling. You know, the IMI has it. There's an ICME. You can find quite a bit of material.
Question from Allison Armour-Garb in New York, asking about what should teacher certification look like in order to encourage modeling? Do you have specific recommendations? We have lots of people representing departments of education here. What could or should be done in terms of certification?
I don't have a quick and easy answer for this one. I really don't. I mean, obviously there are experiences in modeling. I think teachers need to practice it. You need to experience it. You need to actually work in classrooms with it. So I think it's more of a practicum types of experiences where you see where teachers are actually familiar with modeling, actually having to do it, having to teach lessons. I am not an expert in this area, but I do think that you can't just read about modeling. I don't know how else to say it. I think you actually have to do it. I think it's a very hands-on kind of activity. Giving yourself or looking at problems where you don't know where to start and you have to leave. There is also a talent, and there's material about it, but there's also talent in teaching modeling because you want to give time for the students to make mistakes, to go off in the wrong direction, but then you want to bring them back. And the issue, there's a sort of a talent involved in knowing how far you'll let kids go down a path that may not lead them anywhere because you don't have infinite time. There's no doubt about it. I mean, there's something wonderful about modeling problems because students do spend a lot of personal time on it because it's interesting and they'll work on it. And time on task is still crucially important. But it's hard as an instructor to watch students go somewhere where you know that you want to bring them, you want to rein them in a little bit and move them. So but that's experience. There's just no substitute for actually doing it, to actually teach it.
Most of the discussion has been about modeling in high school and undergraduate, but a question also came up about modeling in graduate school. What should be the role there? And also, do graduate schools, in the application process, do they recognize a student's ability in modeling? Should they? Do they?
Well, I can say that students who have done well on the MCM definitely have a leg up. There's no question that it means something in graduate school. In China, if you do well on the MCM or ICM contest, you get free graduate school, you get a job. I get letters and calls from employers literally every day, from China saying, this student came and said they had a meritorious grade on this. Is this true? Because at a certain level, it's an automatic. It's so prestigious there that doing well is almost an automatic increase. But it's the same thing is true to a lesser extent here, in the fact that people who do well on the MCM and the modeling, who show experience, have been able to get hired. I hear these stories all the time. Oh yeah, I took that exam. I did well. It's nice to see how. So there is something through the exams that have been very helpful. But does every math department recognize this work as being, superior? I can't say that, but it's been gradual. You think about when we first started the UMAP Journal, for instance, which had articles about actual student material, teaching modeling examples, articles about teaching modeling. We were the only journal that did that. Now, our editors have to compete with a whole mess of regular college undergraduate journals, because you can publish modeling articles everywhere. So it is changing. There's just no doubt.
So one final question, this from Gary Martin in Alabama. Bringing modeling into the high school curriculum, does that have implications for the relative balance between calculus-centered and discrete mathematics in the high school curriculum?
I think it does. I think that it would argue for introducing some discrete mathematics earlier. I mean, one of the lovely things about discrete mathematics, as I mentioned, is you can get into reasonably sophisticated discussions and arguments with a minimal amount of algebraic manipulative skills. Because after all, if you're worried about plowing your streets, or what's a street network? It's a graph, right? I mean, corners, right? Edges are vertices, and streets are edges, and so with relatively elementary graph theory, you can start talking about how do you get efficiently from point A to point B, and those problems are very real, right? I mean, if you're trying to deliver mail, or you're trying to, if you're worried about plowing snow, well, maybe now you've got a directed graph because it matters which direction you start with. So you can do some very nice modeling problems with a minimal amount of, and more importantly, you can introduce it very early. At what age does a student have to be to see that from point A to point B is a straight line, and maybe you're going to follow a path. So you can do some very nice kinds of things. And I would argue it's useful because the problems are actually quite real, and you can make them fairly sophisticated with a minimal amount of introduction of algebraic content. So yes, I think it might affect the balance. You can always get to the same place. I don't think that's so much the issue, but I think it's much, to the extent that you want students to be able to model interesting things they care about, then I think introducing some discrete ideas early makes a lot of sense.
Well, Saul, thank you so much for your presentation today, and for all the work you've done on behalf of modeling and bringing applications and helping students understand what mathematics is really all about.
Really appreciate the opportunity. Thank you.
You're welcome.